Okay, good afternoon. Today we'll continue discussing recursion, but before we start discussing the recursion, we remind you all that lab test 3 is on Monday. If you register, we have two sessions. We have morning and afternoon. If you register in the morning, please attend the morning session, and we have also afternoon sessions. The main topic that is included in the lab test will be focused on inheritance and time complexity. So the lab test 3 will be similar to the lab test 2 and lab test 1. You will have a programming questions, and you have also multiple choice question. So the most weight will be on the programming questions, okay? And the topics that included in the lab test 3 is inheritance and time complexity. Any questions about lab test 3? When you say just, that mean you should remove all the previous topics. No, it's included everything since we start until we have inheritance, because we're going to focus on the inheritance. Inheritance, that is what it, yes. It's focused on inheritance and time complexity. Okay? So last time we started discussing recursion. Recursion, one of the important topics for advanced Java object-oriented. We defined the recursions. We saw iterative approach and recursive approach to solve some problems. And also we saw many examples, and we trace these examples and find the answers. And also we discussed that whenever we look to design, or whenever we need to trace a recursive problem, we're going to look at at least one base case, at least one recursive call. Today we'll continue discussing recursions. We're going to see what happened to the memory during the recursions. We're going to discuss Tower of Hanoi and the problem, which is one of the famous problems in the literatures. And also we'll discuss the binary search algorithms in the recursive point of view. And we will see the time complexity and how we can analyze the recursive methods to extract the time complexity of the recursive method. And also we will discuss two main yes. Lab test 3, as I mentioned at the beginning, it will focus on the inheritance, programming, and multiple choice. It will focus on time complexity for programming and multiple choice. Okay? So we will discuss Mergesort and Quicksort, one of the famous sorting algorithms. We look at them from the recursive algorithms, how we can design the Mergesort and Quicksort recursively. Just to remind you all, when we say we have a recursive method, we call the method is calling itself. We define that each recursive call should call with different arguments, and these arguments should do some progress toward the base case. If we're not progressing to the word base case, then we will have the infinite recursive call. Each recursive call will have, you can imagine, you have a new code, a new set of parameters, arguments, and also a new set of local variables. So each recursive call, you create a new set of arguments, a new set of local variables. For any recursive method, you should see at least one base case, at least one recursive call. Sometimes we have one or more recursive calls, or sometimes we have one or more base case, but at least one base case, one recursive call. We saw last time this example about calculating factorial 4. Each one is calling another person to find the factorial. So the task is to find factorial of 4. The lady called the brother to find factorial of 3, then factorial of 2, then factorial of 1. We end up with finding factorial of 0. Who is known factorial of 0, which is the base case. Then we call the father to find the factorial of 0. Then recursively, we're going to collect the answer. Then we return to the first method that starts the recursive call. We remind you with power of x, recursive algorithms. Power of x is calculating x to the power of n. Now, we have x to the power of 0 is equal to 1. X to the power of n can be written in terms of x times x to the power n minus 1. So we divide the problem. The original problem was x to the power of n. We write it in terms of itself, but now with different argument n minus 1. If we have x to the power minus n, which is a negative exponential, we will write it as 1 over x of n. We discussed the implementation last time. If n is equal to 0, which is the base case, we're going to retain 1. Otherwise, we're going to check n. If n is positive, then we're going to define it in terms of x times power of x, and we change the argument. You can see here, we start the original call with x and n. Each recursive call, we decrement n. So each recursive call, we are moving toward the base case. And the base case here, n is equal to 0. If we have n is negative, then we call 1 over power of x, and we call minus n. So negative n is become minus n, which is a positive. And next time, recursive call will have n as a positive, and we will end up in the recursive call. Now, we will see today what happened in the memory during the recursion. These recursive call, what are the effect on the memory? Let us discuss a slightly modified version of power of x. Let's say we are discussing power of 10. So if we have power of 10, so we know that x is equal to 10 now, so only one argument is needed, integer n. Now we have the double as the result. If n is less than 0, we're going to call 1 over power of minus n. If n is equal to 0, in this case, we will have the base case. We retain 1. Otherwise, we're going to retain 10 times power of n minus 1. So we modify, and we have another version of power of x, but now we fix x as 10. Having this recursive method, so let's say the main function is there, and we would like to call power of 10 to the power 3. Now, this function is going to start the recursive call. The first recursive call, each time we make a recursive call, we reserve some memory, and that memory is the stack. We have the stack. We store everything on the stack, and we store it in what we call a stack frame. Each stack frame contains information about the method, where is the retained value should be stored, the local variables, the value of the local variables, and where we should retain after we finish the recursive call. So you can think about the stack frame contains all the necessary information to complete the recursive call. Then this access of the recursive stack is very fast, but it's come with the expense that the limit of the stack size is limited. So we cannot do too many recursive calls. Each recursive call is going to store some called stack frame in the memory. But accessing, allocating, and deallocating stack frame is very fast, but we have limited amount of memory for the stack. So if you try to solve a problem that is very large, and you need a very large memory in the stack, will exceed the stack, you will have a stack overflow, and your program will crash. This is exactly what happened when we are doing the recursive call. So each recursive call is going to reserve some part in the memory, and that part is called the stack frame. We're going to store it in the stack, and we're going to build in the top of the stack. Each time we insert on the top of the stack, and if we need to take something from the stack, we take it from the top of the stack. Here is the first call, power of 10 to the power of 3. N is equal to 3. The result will be 10 times power of 2. So now we're going to do the recursive call for power of 2. Another stack frame will be inserted inside the stack. N is equal to 2, which is the argument. Local variable is result, is reserved in the stack. Now the result will be 10 times power of 1. Another recursive call will be made. So another stack frame will be stored in the stack. So N is equal to 1 in this case, and the result will be 10 times power of 0. Power of 0 is the base case. So another recursive call will be made. N is equal to 0. In this case, we have reach the base case, and the result will be equal to 1. Now, all the recursive call is finished. We reach the base case. Now we have to go back and take out from the stack what we insert in the stack frame. The result will be back to the previous call. So 10 times 1, and we remove the stack frame. Again, the result is now 10. It will be back to the previous call, where N is equal to 2. So we substitute the value, 10 times 10, and we remove the stack frame. Then now the result will be back to the previous call, where N is equal to 3. We replace the result 10 times 100, and we remove the stack frame. And the last thing is we're going to back to the main functions, where we call the power of 3 for N. Then we will have removed all the frame from the stack. This is exactly what happened on the memory. Each time you do the recursive call, you store a stack frame inside the stack. Each time you retain from the recursive call, you remove that stack frame. The stack frame contains all the necessary information to do the recursive call. All the local variables, input arguments, where we should back from after we finish the recursive call. All these information will be stored in what we call a stack frame, and this stack frame is inserted in the memory. Any question? Now we will discuss Tower of Hanoi, which is one of the famous problems, but we will look at it in terms of recursive problem, how we can solve this problem in recursive problem. Let us define what is the Tower of Hanoi. We have 3 pegs or bars or towers. You can see in the literature something is pegs. Some people, they call it bars. Some people, they call it towers. And you have N rings. In this case, or this figure on this slide, you have 4 rings. And these rings are small in terms of the diameter. One on the top is the smallest diameter, and one on the bottom, which is number 4, is the largest in diameters. You cannot put one ring larger diameter on the top of the small diameters. You have to put them in order in terms of the diameters, from the smallest diameters to the largest diameters. And the task is to move all these rings from the bar number 1 to bar number 2 with help of bar number 2. So you need to move them from 1 to 3, from the source tower to the destination tower, with help of the auxiliary tower, in this case is number 2. But each time you do the movement, you should not violate the rules. You should not put small diameters below the large diameters, or one of the large diameter on the top of the small diameters. Always the one with the small diameter should be in the top. So this very famous problems in the literatures. The general approach, if you can see, if we can move all, let's assume we can do this. We can move the largest ring, number 4, from the big number to big number 3. But before we do that, all the small diameter rings, we need to move them to the 2. So let us assume we can do this. Let us assume we did this task. So these are 3 rings, we take them all together as a one move. You hold ring 3, all of the rings on the top of it, you take them, you put them on that 2. Then the only movement you need is to move number 4 from 1 to 3. So let's assume you can do this. You can take all these 3 as one movement. With one movement, you take ring 1, 2, and 3. With one single move, you can move them from 1 to 2. Then the next move will be moving number 4 from 1 to 3. If we can do this, we are looking at this problem recursively. We solve it for n, and still we have a problem here for n minus 1, which is in the number 2. So this is the kind of recursive solution. You have a task to move n rings from the starting big to the destination big. Okay? So let us assume we can do this. We can move n minus 1 from the starting one to the auxiliary one. Then the next move will be moving the nth ring from the starting one to the destination. Then the remaining task for us is to move n minus 1 from the auxiliary to the destination. Okay? So we reduce the problem and we redefine the problem in terms of itself. That is the recursive. We start with problem of moving n rings from the source to destination. We redefine the problem. We say that we can do moving n minus 1 from the source to the auxiliary, then we move n to the destination, and then we have another problem, which is n minus 1 now in terms of the size. We have n minus 1 rings on the auxiliary. Our task is taking them from the auxiliary, put them in the destination. So just to demonstrate what we did here, we have 3 rings. This is an example. We have 3 rings on the starting big. We're going to move what? The first one, the smallest one, the green, to the destination. Then we're going to move the red to the middle, move a green back on the top of the red. That is the task. We move n minus 1, which is, we assume we can do it in one shot. So you can see here at move number 3, we are moving n minus 1 from the source to the auxiliary. And the next move will be moving the blue ring to the destination. Now we have to do the job for n minus 1, which is 2 rings on the auxiliary. So we move the green to the source, and red, we move it to the top of the blue, and the last one will be moving the ring. So this is the really 7 movement, or I think it's 7 movement, yes. 7 movement is necessary to move only 3 rings. Okay? Any questions before we proceed? I will repeat this example. So we start with 3 rings. Let's say we start with n at the starting big, and we need to move them to the destination. So we start moving the green to the destination, red to the auxiliary, then we retain the green from the destination to the auxiliary. Now we have moved n minus 1 from the source to the auxiliary. The next job is to moving the big ring, which is the blue one in this case, to the destination. We move the blue one to the destination. This scenario, we are reducing the problem. We just reduce the problem. We complete one movement, which is moving the big diameter ring from the source to the destination. Now we have n minus 1 on the auxiliary. Our task is you have to take n minus 1 from the auxiliary to the destination. You can think now, we reduce the problem from n to n minus 1. To do this, we move the green to the source, then we move the red to the destination, move back the green to the destination. That is total 7 movement. So this is exactly what we discussed in the previous slide. we translate it to the programming. You have to solve the towers. We have start with integer n, number of rings, and from the first tower to the destination tower, in this case 2 towers, and with help of the auxiliary towers. If n is equal to 1, if the number of rings that you have is only 1 ring, then you're going to do only one movement from the source to destination. If you have only 1 ring. Otherwise, that is what we discussed. We're going to move n minus 1 from the source to the auxiliary, then with the help of the destination. After we finish moving n minus 1 from the source to the auxiliary with the help of the destination, we're going to move only 1 ring, which is the last ring from the source to the destination. After we finish moving n minus 1 from the source to the auxiliary, we're going to back again to the problem. We need to move n minus 1 from the auxiliary to the destination with the help of the source. You can see here, we start from the first argument is number of rings. Then we have the source tower, destination tower, and the auxiliary at third argument. See the call, the recursive call. The first recursive call is moving n minus 1 from the source to the auxiliary. Auxiliary is the destination. Then with the help of the 2 tower, which is the destinations. The second recursive call is moving n minus 1 from the auxiliary, which is the source in this case, to the destination with the help of from source. Yes. No, this for n rings. I'll give you here a solution for 2 rings. Just moving 2 rings, and this is the call. You have 2 rings, the source, and based on the argument, this is the destination, and the auxiliary is C. So you're going to move only 2 rings. And that is moving the ring number 1 from A to C, then ring 2 from A to P. P is the destination, then moving ring 1 to the destination. You can take this code, put it inside the Eclipse applications, and run it for any n. And you will see the recursive call and easy to solve the Tower of Hanoi. If you look on the literature, which is not the scope of this course, in the literature, is there any iterative approach to solve Tower of Hanoi? You will find it very complicated, very long solutions. And you can see here on this slide, with a few number of line of code, we solve the problem recursively. The problem here is to think about the time complexity, how much cost effective this Tower of Hanoi. If you see, if we have only to move 1 ring, well, if we have only 1 ring, we're going to have only 1 movement. If we have n rings, that means we're going to move n minus 1 from the source to the auxiliary, and we're going to do 1 movement from the source to the destination. Then we're going to move n minus 1 from the auxiliary to the destinations. So we have 2 n minus 1 movement plus 1, which is, this is the formula. For any n rings, the number of movement, m, of function of n, which is the size of the input, number of rings, is equal to 2 times m of n minus 1 plus 1. Let us take the number of movement for some value of n. If we have only 1 ring, then we're going to do 1 movement. If we have 2 rings, we need 3 movements. If we have 3 rings, we need 7 movements. We just saw that in the previous example. 4 rings, we need 15 movements. 5, we need 31. Did you see the pattern here? The pattern is, for n is equal to 2 to the power n minus 1. 2 to the power 5 is 32, minus 1 is 31. 2 to the power 4 is 16, minus 1 is 15. So Tower of Hanoi is actually the solution with the recursive solution is order of 2 to the power n, which is exponentially in terms of time complexity. Very costly solution. Any question before we start binary search? Okay, to search inside an array or inside the list, either you use a sequential search or binary search. These are the two common algorithms that you can find in the literatures. If you want to go for sequential search, which is the linear search, it's not efficient. And each time you try to check, you're going to eliminate only one element from the array, because you're going to visit everything on the array. And each time you visit, you're going to check if the target you are looking for is the same as the element. In that case, you're going to return true, I find it. Otherwise, you have to keep continue checking. And each iteration, you remove or eliminate one element. But the binary search is more efficient than the sequential search, and it's faster because every time you check, you eliminate half of the array. But there is one thing is a prerequisite for the binary search. The array or the list should be sorted in advance. That's the only preconditions to be able to use the binary search. Why we call it binary? Because each time we go to the array and check for the value, we eliminate half of the array. For the sequential, we eliminate only one, but for the binary search, we eliminate half of the array. So each time we are not successfully finding the target that we are looking for, we reduce the search by 1/2. So if we have a size of the input n, so each time we are not succeed to find the target, we actually reduce the size of input by n/2. This is the linear search algorithm in the iterative approach. So the linear search is start by receiving argument, in this case integer array, and we receive integer targets, the value that we are looking for. Is this target inside this array or not? So we start the for loop. Integer I is equal to 0 until we have the size of the array, and we increment at each iterations. Each time we compare with the element at that index I. If the element is equal, then we're going to retain I, the index where we find the element. Otherwise, we're going to retain -1. You can see here, at each time, we're going to do the sum comparison. If this is a primitive type, we're going to do equal, equal. But if it's object, we're going to do x dot equals, and we give the array element. So in the linear search, we need n comparisons. So it's a linear time complexity. So the recursive linear search algorithms find the target or until we reach the end. This is the base case. If we need to find the recursive call or design the linear search recursively, so find the target or reach the end of the array. Recursive call the linear search with array for the index less than where we are reaching until the end. So this is the example for implementing linear search recursively. You can see here we introduce a new argument, which is the low, integer low, which is represent the index that we start with. So you start receiving array, index low, and integer x, which is the value that you are looking for. If the index now you are pointing to the element that is greater than the length, that means you couldn't find the element that you are looking for. So this is one of the base case, you reach the end of the array. If you find x is equal to array at low index, okay, then this is the base case. You find the target that you are looking for, you retain the low index. Otherwise, you're going to do the recursive call, you send the same array, and you send low +1. You move the index one step at a time. And you call it with the same x. So you can see here, each recursive call is making one step toward the base case. The base case here in this case, either to find the target that you're looking for, or you reach the end of the array. This is the recursive call where the low plus 1 each time is an increment. So you start with the low pointing to the index at 0. You check array at 0. You couldn't find the index. Then you do the recursive call with the same array, but now you call for index is equal to 1 with the same x. You keep doing this, incrementing the low index until you reach the end of the array or you find your element. There's nothing different. Even this with more overhead. Linear search will not use the for loop, will not use the stack to store the stack frames, each recursive call. But this implementation is to show you that an iterative approach for the linear search can be implemented recursively. Now, in terms of the cost, time complexity, they are the same time complexity, because the worst case you have to do n comparisons. Now, in terms of the overhead and memory that is needed to compare between iterative approach and recursive approach, this you need more memory on the recursive code, because you need to stack and you need to store stack frame at each recursive code. In the iterative approach, you don't need that. You don't need to store a stack frame at each iteration of the loop. Any other question? You want to do low is equal? Why? You're going to start from low is equal to 0. At each recursive call, you increment index 1, 2, 3, until you reach the length of the array. Let's say you have an array of 5 elements. 0, 1, 2, 3, 4. The last element is 4. The length of the array is 5. Okay? So if you have low is greater than or equal to 5, then you're going to stop. Okay? Now, if you would like to start from the end of the array, then you have to change the base case. In this case, you start from length minus 1 and until you reach the low is equal to 0. It's different implementation. But you're not reducing the time complexity or doing it think fast, because still you have to do n comparisons. Yeah, the same, either to start from the beginning of the array or the end of the array. Binary search is different. Binary search requires that the array should be sorted in advance. And that is the only things is needed to use the binary search. If you try to use the binary search with unsorted array, you might expect it you can see unexpected results. Okay? So let's say if you are looking for the value of 42 and you have the array of from 0 to 16 elements, so that means array of length 17, okay? You will start putting index, one index at the minimum at index 0, one index at the maximum at 16, and then 0 plus 16 divided by 2, you take the ceiling or the floor to find the middle. Then you put index at 8. Now you check if the target that you're looking for, 42, is less than the value at index 8 or greater than the value at index 8. If it's greater than, then you're going to remove all the previous from the minimum to the medium. All these half, we're going to remove it. If it's less than, then you're going to remove the upper part. So the value 42 is greater than the middle, greater than 30. So we're going to move the index. So the minimum now is pointing to middle plus 1, which is 9. And we calculate the midpoint, it will be 12. We ask if 42 less than 56, that's true. Then we're going to remove the upper part. In this case, the middle will be pointing to the 10. If we ask the middle is 42 at index 10, that's true, then we find our value. So each time you do comparison, you remove n over 2, half of the array or half of the input set. If you start the input with 17 elements, at each comparison, you remove 17 over 2, the first one. The second one, 8 over 2, and then the rest 4 over 2. This is the binary search implemented iteratively using while loop. You can see here we have received input, array, and the target. We start by putting the indices, index for minimum, index for the maximum. And the index for the minimum is 0, which is the point to the first element of the array, and the index of the maximum is pointing to the last element of the array. Now, we calculate if the minimum is less than the maximum. In this case, if we are looking for the element and the index, which is the minimum index, in this original case is 0, and the maximum is length over 2, if the minimum is greater than the maximum, we stop. Okay? Otherwise, we're going to continue inside the loop. Minimum is less than the maximum. So the minimum, we calculate the middle point, minimum plus the maximum divided by 2, the middle index, and we compare with the target. The element of the array at the middle point is less than the target. If it's less than the target, we're going to revise the minimum index by putting it to the middle index plus 1. If the middle element is greater than the index, greater than the target, we're going to revise the max by putting the max index to the middle point minus 1. And otherwise, we're going to retain the middle point. That means we find the target, we retain the middle point. If we keep doing the loop and we not succeed to retain the target, we're going to retain the minimum plus 1. All is minus 1. So if we do the binary search recursively, if we call binary search for the data for 42, we retain 10. If we call the binary search for 66, we retain minus 14, where the 66 should be located, plus 1 minus. To be able to do the binary search recursively, we cannot do it with one direct recursion that the method is calling itself. We need to define a helper method to allow us to do this recursive call. So we start with public, static, integers, binary search. We receive the array, and we receive the target. Then we call a helper method, binary search, with the same name, but it's different signatures. But this is a private helper method to help us to find the target. The argument for the binary search helper methods is the array itself, the target, and integer min and integer max. Integer min and max are the indices for the array. If the minimum is greater than the maximum index, then we're going to retain minus 1. Otherwise, we calculate the middle point, and we compare the middle point with the target. If the middle point was less than the target, then it's too small, go to the right. We're going to go to the right. That means the target is greater than the middle point. You can see here, we do the recursive call. We're going to call the binary search with the same array, the same target, but with different indices. The middle plus 1, then we keep the maximum, because we're going to go look at the right side. If the middle was greater than the target, we're going to look at the left side. So we're going to revise the array and the target, and we're going to adjust the indices. The minimum will stay the same, but the maximum will be the middle minus 1. Otherwise, we're going to retain the middle. The target is found at the middle point. each time. Each time you want to say the length divided by 2. But we're not changing the array each time. The array is fixed. So array.length is fixed. You have to make sure that each recursive call is doing progress toward the base case. And the base case in this scenario is the minimum is greater than the maximum. That means you keep adjusting the min and the max index, okay, until you find the target or you reach the minimum is greater than the maximum. In this case, you retain -1 where the target is not found. Okay? Any other question? Okay, so sometimes it's interested and it's actually is not sometimes, it's very important to know how much time complexity of this binary search. So each time the input array of size n, we divide it by 2. So we start with n, the next call is n over 2, the next one is n over 4, n over 8, until we have one element. You can think about it here differently. How many times I need to divide by 2, multiply by 2 until I reach n? So 1, 2, until I have n. So if we have 2 to the power x is equal to n, so log of 2 base 2 to the n is equal to x. So we have time complexity is logarithmic. So if you have a loop and each time in this loop you divide the size of the input by 2, okay, then you have a logarithmic log of n to the base 2. So the binary search will be log of n plus 1. 1 is not important, but it's the last comparison in the worst case. And the linear search is n, linear time complexity. So the binary search is very fast, but need array to be sorted in advance. Just to look at the numbers to see how much the binary search is faster than the linear search. If you have an array of size n, you might not see that much difference. The linear search will take 10 units of time, and the binary search will take 4 units of time. But if you have an array of 1 million, you will see that difference. That's 1 million units of time for the linear search compared to 20 units of time. 10 millions, you need 10 million units of time for the linear search, while you need actually 24 for the binary search. But the only thing for the binary search, you need to sort the array on advance. Okay? Here is an example to demonstrate the power of binary search. You need to look inside this array for 65. So you start by taking the lower index 0 and 285 divided by 2. So the middle is 602. You compare it with the target that you are looking for. So the target is greater than 602. Then I will remove all the lower half. All these lower half will be removed, and the indices will be adjusted. So now we have the middle is 85. Now, it's 85 is greater than or less than the target, is greater than the target. So we're going to remove the upper half. We adjust the indices. The index now pointing to 708. 708 is still greater than the target. So we're going to remove the upper half. Now we have 63. 63 is less than 65. So we're going to remove the lower half. We adjust the indices. And again, 66 is greater than 65, so we're going to adjust the indices to point to 64. Then we keep doing this until we have the value that we are looking for. So we actually need 8 operations, okay, 8 comparisons to find the element inside array of 285 elements. And this array is sorted in advance. Now, back to the sorting algorithms. We have actually two main sorting algorithms that we can solve them recursively: Mergesort and Quicksort. Okay? Mergesort will take the array and divide it to parts and then sort each part individually, then collect the results. Quicksort will try to take a value as an index and try to sort based on this value. So as we saw in the binary search, is very powerful, but we need the array to be sorted. So let us look here about two kind of methodology or two algorithms recursively, how they can sort any array. By the way, if we saw the example here for integers, that doesn't mean this binary search or merge search, merge sort or binary sort, search or quick sort work only for integers. You can work with any primitive type, with any objects. But the only thing that you have to take care of, whenever you need to sort object that you have created, you have to implement compare to correctly. So you can sort this object correctly. Now let us go to the merge sort. Merge sort have a concept of divide and conquer. So you divide the problem, then you try to solve the small version of the problem. That is divide the array in halves and merge sort each halves. That is decompositions. Then combine the sorted halves. That is a composition. Now, what is the base case? The base case, if you have an array of one element. If you have an array of one element, is already sorted. Now, it's hard to implement iteratively, but it's very easy to implement recursively. Let's see, here is the trace of execution for the merge sort. Let's say we start with this array, and we need to do merge sort algorithm. So we're going to divide the array on halves, keep dividing on halves until we have the base case. What's the base case? Is array of one element. 3 is array of one element. It's already sorted. 6 is array of one element. It's already sorted. Now, once we reach the base case, so that means all the elements on the base case are already sorted. Now we have to do compositions. We have to collect them back. So we look at the 3 and 6. Which one is the less than each other? So 3 is less than 6, so 3 should come first. So we group them together. 4 and 2, or 8 and 2. So we sort them again. We have only 2 elements. We need to check them. So we check 3 and 6, 3, 6, then 8 and 2, 2 and 8, and 4 and 5, then 1 and 7. Again, now we're going to look at the array of bigger size, array of 2 elements. But these elements inside these arrays, now it's sorted. Okay? So we're going to look at the element 2 and 3. Which one is the smallest? Is 2. So we're going to take 2, put it in the middle, in the beginning, then 3, 6, and 8. So you can see here, we solved the small version of the problem where the element is only 1. Then we have 2 elements, but these elements are sorted. And then we start with a bigger array until we reach the original problem. So you see that you have forward directions and backward directions. The forward directions is just dividing. You're not doing anything. Just divide the array. If you have n, you have to keep dividing on half until you have one element. Then the next one is backward, how to aggregate and collect the results. You have to do the comparisons for n. This is an example how you can sort array of 2 elements. You want to group them. So you put index at the first element and index at the second element. You check 2 and 3. Which one is less? 2. So you're going to take 2 and advance the index for the second array. So we started 2. Now we have it here. Now we check between 3 and 8. Which one is the smallest? It's 3. We're going to take 3 and advance the index. Now between 6 and 8, we have 6. So we advance the index, finished, but we left only one element for 8. We take it. So this is how we merge 2 arrays of 2 elements. Okay? and you can expand this for an array of n elements. So how many comparison we need? If we back to the beginning, how many comparison we need? If we have element of 2 array, 4 comparisons, okay? So we need 4 comparison to be able to sort array of 2 elements. This is another example of merge sort. The first iterations, they receive the array, you divide it on halves. You keep dividing until you reach the 1 element. This is the base case. Now you reach the base case. The next iteration is sorting. You need to sort this. So you sort 2 and 8, 4 and 6, 5 and 3, 1 and 6. You end up with 4 segments. Each segment is 2 elements. But these segments are already sorted. Now you merge them again. The same methodology. You see here how many comparison I need to merge 8 and 2. 1 comparison. Here 1. Then this is 4, and then we end up with array. So this is like a forward direction and backward direction, or what we said, decompositions and compositions. You break it, okay, divide and conquer. You divide the problem until you are able to solve the small version of it, which is 1 element. Okay? Let's see. No. Even if you want to make such kind of conditions, array length should be even. You can add a dummy elements, a null elements, okay, in the array. You have odd, okay? You can add any elements on the array to make it, okay, even. But there's no preconditions on the length of the array for the merge sort. Yes? You have 2 elements. You have only 2 elements, x and y. How you sort them? You have x and y. You have 2 variables, x and y. To sort, you have to compare. You have 2 elements. You have x and y. You have only x array of 1 element. X array where is only 1 element. Y is another array, only 1 element inside it. How many comparison you need to do? Oh, if y has 2 elements, you have to go to the previous slides. Here I show you example of array. You can see here. This is x, 2 elements. This is y, 2 elements. How I merge them together? I put the pointers at the beginning of x, pointing at the first element of x. I put the pointer at the beginning of y. I ask, 3 is greater than 2. Then I say, no, 2 is less, so I pick 2. Then I ask, 3 is greater than 8. No, 3 is less than, so I pick 3. I move the index to the 6. Then I ask, 6 is less than 8. No, 8 is greater than 6, so I pick 6. Then I keep doing this until I have to merge. And what I saw, or what we saw on the previous slide, is example of merging array of 2 elements. You can take this example and put it for array of any size. Okay? So, for the merge sort, if you have as array more than 1 element, so you're going to take the first half, you call it the front. You're going to take the rest of the array to call it the tail. You're going to merge sort for the front and merge sort for the tail. Okay? That is the recursions. You start with array A. You divide it on half, the front and the tail. You do the merge sort for the front, and you do the merge sort for the tail. And once you finish, you merge the sort, the front and the tail together. Otherwise, do nothing, which means you have an array of 1 element. That is the base case. So here is the merge sort code. You can see here the for loop. We are using for loop. That means this is a recursive implementation or iterative implementation. Iterative implementations. So you can see here we have the left and right, okay? We ask, we have I1, I2, and this iterative implementation for what? Merge. We merge the array. So we assume that we receive the left and the right, and we have to retain the result on the result array. So we ask, we go through all the elements inside the result. We have to fill this element. If I is greater than the right length, or I is less than the left length, and I left length is less than the right, okay, then we're going to store the left element. Otherwise, we're going to store the right element. This is simply the merge between two arrays sorted. So you have the left half is sorted, the right half is sorted. You go through the loop, okay? If the element inside the left half is 10, the element on the right half is 20, so the result should have 30 elements, okay? The merge sort, in this case, if the array has a length is greater than or equal to 2, then we're going to do first half. We're going to take from 0 to array length divided by 2. We do arrays.copy range. We take all the elements from A for the first half, the front. We put it on the left. And we take the second half, we put it on the right. We do the merge sort for the left half and the merge sort for the right half, and then we call the merge. The merge is to merge these two arrays together. Otherwise, we're going to do nothing. So that means if the array length is equal to 1, which is 1 element. Yes, you compare each element, yes. And I have to go if the element, I said, if the element on the left, on the front, 10 elements, on the tail, let's say 12 elements, that means I have to go through 10 plus 12 comparisons. Any question about the merge sort? You just take the array, divide it into half, then you call the merge sort for the first half, then the merge sort for the second half. Then after you did this, you have to merge them together. Here is no recursive. That's the base case. If this is true, then we're gonna do any recursive call. If the a.length is equal to 1, there is no necessary to do any recursive calls. Here we do the recursive call for the left half, sorry, and the right half that make a smaller array. That's each recursive call make a progress toward the base case, which is reducing each time we reduce the size of the array. Now, we combine the two sorted array using the merge algorithms. Regarding the merge sort runtime, okay, the worst case of comparison of the array, you need to compare the array. Yes, you have received the sorted array, and you need to go over the for loop to compare the element inside the array. Nothing we need to do during the decompositions. Once you receive the array, you divide, just divide. There's nothing we need to do. Just take the array, take the front half, take the tail part, okay, and then call the merge sort. This is a process of decomposition. You're not going to do anything. When you need to merge sort this array, you need to do the comparisons. So if the array size is n from the two sorted array, the size n over 2, then you need n minus 1 comparisons. So if the front array is sorted with size n over 2 and the tail is sorted n over 2, then you need n minus 1 comparisons. So let us assume, without lose any generality, that n is actually power of 2. So the merge algorithm is splitting the array in two halves and then call recursively to do the merge. So if you have time complexity for the merge sort for array of size n, simply you have the time merge sort for n over 2 plus the merge sort for n over 2. The first n over 2, the merge sort for the front, then the merge sort for the tail, plus the merge time, which is once you receive the array is already sorted, you need to merge them together. So the first one is T of n, or is the time for sorting the first half, and T of n over 2 is the time for the second. To the merge two arrays, you need at most n minus 1 comparisons. So you have 2n minus 1, okay? And you have, here is the formula for the merge sort. You have 2 for time of n over 2 for the merge sort for the first half and the second half, plus 2n minus 1, okay, for the comparisons to merge two arrays. So let's say, because 2n minus 1 is the numbers is not that important, let's approximate this to T of n is approximated as T over n over 2 plus n. So this is the first call. You start with an array of size n, then you divide it in two halves. You need the time complexity for the first half and the time complexity for the second half, then 2 times T of n over 2. The second call will be 2 times, you just substitute n over 4 plus n over 2, because the array size is reduced by 2. Then you have 4 T of n over 4 plus 2n. If you have one more iteration, then you have T of n over 4. You substitute now, you divide the array by 2. So then you have n over 8 plus n over 4. You substitute it inside T of n over 4. You will end up with the formula 8 times T n over 8 plus 3n. Then if you keep doing this, you will see the pattern. The pattern is 2 to the power k T of n divided by 2 to the power k plus kn. That is the pattern to do the merge sort, the time complexity for the merge sort. How many operation we need to complete the merge sort for array of size n. So if we try to solve this problem and we assume that n is power of 2, so 2 divided by 2 to the power n is equal to 1, then 2k is equal to n, and we have k is equal to log 2 of n. If we substitute this inside the equation, we end up with n times t to the power 1, because we have here 2n divided by 2 to the power k is equal to 1. So you have n times t to the 1 plus n log 2n, using this fact. That's 2 to the power k is equal to the power log n is equal to n. And end up with the formula that n is equal to n log n. That means the merge sort is actually linear logarithmic time complexity, n log n. So all these time complexity analysis for the recursive call. We start by n. At each iteration, we divide n to 2. That means we need n over 2 time complexity, okay? But we need n comparison to merge the two part of that array until we end up with the formula t to the power n, t of n is equal to the power of k times t to the power n over k plus kn. We analyze this, we end up with time complexity for the merge sort is n log n. Now we will start the Quicksort algorithm. Any questions about the merge sort? Yeah. You're supposed to know how to calculate the time complexity of a recursive algorithms. Now, what we did here is we analyzed the merge sort step by step. We start with n array. We divide n to 2 halves. You can see here the time complexity 2 of n to do the merge sort for array of size n. At each step, we divide the array in 2 halves. So we say if we have a time complexity for n, then it should be equal to the time complexity of n over 2 plus time complexity of n over 2 plus the time to merge these 2 halves together. Okay? Now, how many operations I need to merge 2 halves together? If I have the first half n, the second half is n, then I have 2n minus 1. Okay? Now, we end up with this formula. This formula, to get this formula, is not so much hard. Okay? The time complexity, T of n, which is the time complexity to do the merge sort for array of size n, is equal 2 times the time complexity to do half of n, n over 2, plus 2n minus 1, which is the time to do the comparison. To merge any 2 arrays, they are sorted of size n, you need 2n minus 1. Okay? We say that let us forget about 2n minus 1. Then we start doing the iteration. This is a process of substitution. If you start with array of size n over 2, then what's the next iteration will be? N over 2, you're going to divide it to 2 subarray, n over 4, n over 4. The time complexity to merge sort n over 2 is actually 2 times n time complexity of n over 4 plus, if you have 2 arrays, n over 4, and you need to merge them together, you need n over 2 times. So all these steps is just to show you step by step how we end up with this formula. T, time complexity to merge array of size n, is equal to 2 to the power k times the time complexity of n divided by 2 to the power k plus kn. If the question is, I need to know this, you need to know this. You need to derive it. Yes, you need to know how to derive it. Okay? There is nothing magic on this slide. Maybe the number going to scare you, but these are just very simple substitutions, okay, to find the final answers. Okay? Even sometimes, if I give you the algorithms, I ask you about the time complexity. If I ask you about the proof, you have to show me all the steps. If I ask you what is the time complexity of this algorithm, it's a linear time complexity of n or O of n log n. Just give me the answer. You don't need to show me how it's your work. Okay? But if I ask you to show you all the steps of your work, you have to show me all the steps. How you come with this recursion. Because this is a recursive formula. This is a recursive formula. Okay? This is a recursive formula, okay, or a recursive function. You already know the recursive function from the discrete math. Okay? In discrete math, you know the recursive functions, okay, and you take a lot of series to find the recursive functions. Okay? Yes, 2n minus 1. I focus on the dominant terms. Okay? You just focus on the dominant terms. And it's coming from the best practice. There's no magic rules. I tell you, okay, if you see this, do this. No, it's coming from the best practice. And normally, if you go to the literatures, for the people who derive, I recommended all of you to go to the literature, see how the time complexity of merge source and how the people are deriving the equation for that time complexity. You will see different approaches, okay, but all of them end with the same results. Okay? Without losing any generality, you can assume n is equal to the power of 2 for simplicity. You already in discrete math, you already take a proof, okay, where you are proving without loss of generality something about the input arguments. Okay? You can take n power of 2. Assume it. It make it simple for you because in the calculation you see here 2 to the power k t of n divided by 2 to the power k, which is give me an indication that if I assume the n is power of 2 will simplify the calculation for me. Now I end up with the result here, n log of n, without any assumption that n could be power of 2 or maybe not power of 2. Okay? Any other questions? Okay. We'll start introducing the Quicksort. Maybe we're not able to complete it today, but we'll start introducing the Quicksort. We'll complete it next time. Now, the Quicksort also follow the same paradigms for the Mergesort, divide and conquer. We try to divide the problem to smaller problem, and that is really exactly what the recursive approach is doing. So here is the problem here. We start partitioning. We have array start from P and R into possibly two non-empty array that has P to Q minus 1, then we have Q plus 1 to R. So you can see here we divide the array in two arrays. But what is Q and what is R and all of these? So all the element on the left side, which is from P to Q minus 1, all the element in that half less than the element at Q. How I pick a Q, we're going to come to that question. Okay? Now, at the Q, all the element from Q plus 1 to R to the end of the array is greater than Q. So simply you're not sorting thing. You just take a value, you pick index on the array. I pick this index, Q. How I pick it? What is the criteria should I pick the Q? All of this is different in the literatures. Many suggestions, many research to find the best Q to pick that element. But let's assume that you go to the array, you pick any index. You may be generated randomly using random functions. You go this index, you pick the value at that index, you try at the first iteration to partition this array where the left side less than this element, where the right side greater than this element. I'm not saying sort them. I'm just saying this constraint should be valid. All the elements on the left side should less than the element at Q. All the elements on the right side should be greater than the element. They could be not sorted, but at least the constraint is valid. So the concourse is sorting two subarrays by recursive call to the Quicksort. Combine the subarray sorted in place. No work is needed. See the difference here? In the Mergesort, you divide, then after you finish division, you start sorting and merge. Here, no. While you are dividing, you're actually sorting. Then once you need to merge them, you just put them in the place. Everything is on the right place. So let's say you give an array of S to be sorted. If the size of S is less than 1, nothing to do anything. The size is 1, so only one element. If the size of array is greater than 1, pick element V, which is call it above it element. Okay? Pick element, any element. Where is that location of that element? Any locations. Just pick one. Once you pick it out, you start to partition. Take all the array S minus this element, okay, remaining in two subgroups, okay, where all the element, okay, on S minus V smaller than this index is smaller than the value at V, and where S2 all the element is greater than the value at V. And then retain the Quicksort for S1 and S2. You have now two sets where the element on S1 less than the element at V, and S2 all the element is greater than the element at V. This is an example. By example, it's make it more easy and clear. Let's say I will pick the first element on the array. That is my choice. Maybe you decided to pick the last element on the array. It's your choice. In the literature, there's a lot of research which is the best element. Remember, your receive array is not sorted. You don't know anything about this array. The computer will do the quick sort for you, but with some instructions. What is this instruction? Pick an element. In this case, I pick 40, the first element. Now, what should I do the next step? Is trying to partition this array in two halves. The first half, all the element less than 40. The second half, all the element is greater than 40. So let us start. Okay? We start. The pivot index is equal to 0. That means it's the first element. Okay? We start from element 2, because element 2 is the next element. Is 20, that's 2 big index, and this is 2 small index. You see, 2 indices. 2 big, 2 small index. So, while loop, while the 2 big index is less than the value at the pivot, where the pivot here index is equal to 0, we're going to increment the 2 big index. So let us see. Do the while loop. So if we do the while loop, we keep in increment. So 2 big, that's 20. We start 20. Okay? We point at 20. Is it 20 less than the 40? Yes. 20 is less than the 40. So we're going to increment 2 big index. Another location. Is 10 less than 40? Yes, we keep increment. Is 80 less than 40? No, we stop. We're going to start another loop. We look at the index of 2 small. Is the value at 2 small is greater than the value at the pivot index? We're going to decrement 2 small. Now you can see here, 100 is greater than the 40. Yes, so please decrement 2 small. 30 is less than 40. Yes, we're not going to do any decrement. We're going to stop. We're going to start now swap. We're going to swap the one at 80, the index, 2 big index, with 2 small index. So if 2 big index less than 2 small index, that's right. Index at 3 is less than index at 7. So we're going to do swap. We're going to swap the values. So now this is 30 and this is 40. And we're going to try to repeat the loop while 2 small index is greater than 2 big index. Go to step number 5. Go back again. We're going to do the same loop. Now again, 60 is greater than, we're going to stop. We're going to go back again. If the 80 is greater than 40, yes, we're going to decrement. 7 is less than 40, we're going to do the swap in this case. Keep doing this. Then go back again to the while loop. 7 is less than 40, that's okay. We're going to increment. Now 50 is greater than 40, we're going to stop. We look at this 2 small. 2 small is also 60 is greater than 40. There's no decrement in this case. We're going to stop. Now we have 2 small less than the big, which is the one here. 2 small is greater than 2 big index. Now we're going to do the step swap. You can see here, we're going to swap. What is the value here? With the 40. Now you can see by finishing all these while loops, we partition the array. I don't say that due to the partition that the left side will be sorted. No, I guarantee to you that the left side will be all the values less than the pivot value. In this case, all the values on the left side are less than 40. All the values to the right side are greater than 40. Now, you can see we partitioned the array. Now we're going to do the quick sort again. We're going to call the quick sort to do the sorting again. We leave you to this point, and we will continue next time about the quick sort and discussing more about it.